Hi, this is a continuation for power electronics module, and this is the task 3 in lab 1. In the previous task 1 and task 2, we discussed brief about LTSpice and how we use it to generate IV curve for resistor and diode. And this video is about sources. So we have sources and we know how to install this source, but sometimes we used it as a fixed voltage. But in this video, we are going to use it in different way. So if you just try to click on this source, okay, and you go to the advanced option here, okay, a new window will come up. This window shows to you different options of voltages or maybe signals that you can generate instead of just a DC value. If you want just a DC value, just go to none and just put your DC value there, like 10 voltage, for example. But in this video, we're going just to see if we can really do other things. So let's start with the first one, which is pulse. I'm not going through all of them. I'm just going through some common signals that we are going to use in our module. So the pulse is a train of pulses, okay? You have to specify the frequency, the on time and the off time, and the value 0 and 1, okay? So it says here, what is the initial value for this pulse to start from, and we used to initiate from 0 volt. And what is the on value when it starts from 0 and go to 1, okay, logic 1? So what is the on value? Sometimes we use like 5 volt usually, okay, but in this simulation we are going to use 10 volt because our initial source is 10 volts. So I wanted to jump from 0 to 10, 0 to 10, okay? And now it asks about the delay, how much delay until it starts pulsating, okay? And I will say I want it as 0. What is the rise time, okay, when the signal go from 0 to 1? This is rise time. I want it as short as possible, so I will set it to 1 nano for example, or 1 pico, but leave it as 1 nano. The fall time is again 1 nano, and the on time and the period. So the period is the period of the signal which sets the frequency. If I want the frequency to be 1 kilohertz, so the period will be 1 millisecond. If the frequency is 10 kilohertz, so it will be 100 microseconds. So I will set it to 100 microseconds because I want my frequency to be 10 kilohertz. The on time and the off time, if you set the on time, it will be automatically set the off time. So I will choose 50 microseconds as on time, which will be about 50% duty cycle. And this is the number of cycles. If you want it to be repeated forever, so don't insert any number here. If you want it just to be inserted for to be run for few cycles, maybe 10, 100, 1000, so you can write a number here. I will leave it as it is and make OK. Okay, so this is now the command, because there is overlap between this and the other components. You can really move it by these two here, okay, and make it like that, right? So this is now the pulsating source, and these are two resistors as before. I will run now the simulation, but I have to edit the simulation command to be transient. For example, because now the duration of the pulse is 10 microseconds, okay? If I choose in here 1 millisecond, it means that it will show for me 10 cycles. Remember to make it 1 milli, not just 1. 1 is 1 second, and 1 milli is a millisecond, okay? And just I press it there, and now run, okay? So now the time domain is set to be 1 millisecond, okay, and now the run is complete. So I can now choose what is the value or the signal that I want just to show. I will show the source value, which is this one, press, and I have it here. I can rescale this one to be from 0 to 20, just to make it easy for us to know what is the peak value. And yeah, it shows for me about 10 cycles, because 1 millisecond has 10 cycles of the 100 microsecond. And that's it for the pulsating. So we can use this pulse source for PWM generation as well by changing the duty cycle here, 50 microsecond, to be less or higher. Okay, and for the output it should be half of this pulsating. I will just press on this, and yes, it's half. Okay, so the purple one is the V output, and the green one is the V source. I dislike that it rescale by itself. It doesn't maintain the same voltage scale here for every time, but it's okay, no problem. So here's what we got for pulsating. As addition, we can really ask LTSpice to measure for us the average value and RMS value, for example, for the V out. Okay, so now if I go to the waveform name and press Control key on the keyboard and press then the mouse, it gives me here the average value. See, the average value is 5 volt and the RMS value is 7 volt. Now let's focus on the average value. The average value is 5 volt, which is reasonable because we have 50% reduced cycle of the 10 voltage, which is half. Okay, so it's the 5 volt. Now what is the average value for the V output? Let's now check by going on top of the waveform name and control and press again. It gives us 2.5 voltage because the average value here is divided by 2 resistors. Okay, voltage divider, and we got 2.5. So by pressing Control and just press on the name of the waveform, you can get more information about RMS and average value. The same can be done for the current. So I will just draw the current for R2, for example. Just press on this one, and you have the waveform in red. Okay, so the current is on the right here from 0 to 5 milliamp. I can just hover over the name and press Control and press this one. So it gives me now 2.5 milliamp as average value. If I want to get also the power dissipation, Alt key and over the component you can press, and it generates for you the equation. And by Control, press Control, and on the top of the name of the power equation, which is the instantaneous power, this one, it gives you the average power in milliwatt or in watt here, which is 12.5 milliwatt. Okay, so it calculates for you. It made the integration, as we learned in power electronics lectures, that the average power is the integration for the instantaneous power over a cycle. Okay, and we have 10 cycles here. The LTSpice can recognize that and really measure the average value. Okay, so this is the thing that you have to duplicate now before going to the next step. So let's now go to a different type of waveforms. I will choose now sine wave. I think all of you are aware about sine wave parameters. We have something called DC offset, which is the DC offset of the sine wave 0, or it's shifted up or down. The amplitude, leave it as 10, which is the peak value. The frequency here is 0. I can set it to like 10 kilohertz. Okay, and the time delay and phi in degree. Okay, let it 0, which is the phase angle, and number of cycles, just leave it as empty, and theta, leave it as empty here. Okay, so you don't need actually to fill all the spaces. Just give the maybe main spaces that it requested. Okay, so we will see now if it's asking for any other parameters. I think it's okay. We can run now, and yeah, it's running and giving all the signals now, converting the pulses to sine wave. I can zoom by just going through this, yeah, and zoom again and zoom again. Okay, now if I want to calculate the frequency or the duration, for example, I want just to introduce to you another property here for the graph. Okay, look at this space here. Okay, this corner, right? And I want to make a square by the mouse, but don't leave your mouse button. Just press like that from this peak to that peak, for example. Okay, and don't leave your mouse button. Look at the corner. You will find something like dx equal 50 microsecond. Dx, which is the difference between the first point and the last point, in time, because the x-axis is time, okay, the difference between this point and this point is 50 microseconds, okay. And also it gives you the y-axis. If you want to measure the peak-to-peak value as well, you can do that. If you release your mouse button, it will zoom. But if you press now escape in the keyboard, it will just cancel the zooming or the command. Now I want to know the peak-to-peak value. I just go to this peak and go to the second peak like that and read the value in the dy. dy says it is 25 milliwatt and also 20 volt and also 10 milliampere. So it depends on what waveform I'm interested in. I can get the peak-to-peak value from these three values, okay. For the frequency, the frequency is from peak to peak, okay. You can get the duration. So the duration now is about 50 microseconds, and I can really get the frequency by reciprocate of this one. And remember that this waveform, which is the blue one, is not the sine wave that we have got, which is 10 kilohertz. This one is for the power, which has double of the frequency, okay. So if you go to the red one, which is this one, from this peak to that peak, okay, you will get about 100 microseconds, which is the 10 kilohertz signal. And your task is to duplicate what I have done now. Let's go to another one, which is I don't want to go for exponential, and this one I will go through the PWL. What is PWL? It's piecewise linear function. Piecewise linear function, and this is very important one because sometimes you want to make up a waveform that's not part of the previous one. So it gives us here a table, and if that table is complex for you to understand, we can go to additional PWL points, and that is more important for us, or maybe easier for us, okay. So at 0 time, I'm telling what is the value. Okay, let's say 0 volt. After that, I want, for example, because we have duration of 1 milli, okay, so I can say about 0.2 milli. I want the value to be 10, and maybe 0.5 milli. I want it to be 5 volt, for example, and then 0.7 milli. I want it to be 8, and then at 10 milli or a 1 milli, I want it to be 0 again, okay. So after pressing, so I'm telling the LTSpice how to reshape or to generate my signal point by point, and press OK, and then press run, and this is my signal, okay. Because my time domain here, or my time axis, is just 1 millisecond, and my points I fed here is just 1 millisecond, so it exactly shows what I already fed, okay. So this is the waveform, initial one, for the current and for the voltage and also for the power. I can remove all of these, just if I want just to make Vs as the one showing here without deleting every one here. I just will double click on the Vs, double click, and it shows for me just Vs. If you double click on the waveform name, it shows you just only waveform that you want, okay. So this is the voltage waveform, and it's exactly what we want. But what if I made the transient here to be, for example, 10 milliseconds and run again? What happens now? It shows for me the signal to be just for 1 millisecond and make it 0 for the rest or the remaining of the time, okay. If I want to make it repeated, okay, I have to add one more thing. I will just shift that here, okay, just to make it clear, and right click on this one. It shows for me this example, this command, and I will add a new thing here. What is that one? I will say repeat forever, okay, and at the end of this I will make end repeat. So LTSpice is running the PWL but in a repeated ways, like for loop, infinite for loop, forever, until I have the 10 millisecond or more than this. So let's just make OK. So here is my command, piecewise linear signal, but repeat that signal forever. If I want to repeat it just for 5 times, I will show you now. Okay, so let's now run. Yeah, I have it now. Okay, I have the signal and for infinite time. So you don't need actually to generate it for every time after the 1 millisecond. If you want to repeat this signal just 5 times, for example, not 10 times here or forever, I can just change the word forever here. Okay, so instead of forever, I just will delete the word ever and make space and make it for 5 times. Okay, so the new command now repeat for 5 times and end repeat. Now let's run it, and yes, it's 5 times now. Okay, if you made any mistake, LTSpice will tell you that there is a mistake. For example, if I forgot the word for, so repeat 5, okay, and I want to run it, it tells you here that it's not expecting just 5, it's expecting repeat 4. So there is a word for is missing here, so I can rewrite it again here, the word for 5 times, and it will show me the same signal. Now there is an important point here, how LTSpice measure the average values. Okay, if I want to measure the average voltage out of this signal, okay, as we said, we can go and we just after we run it, okay, we just press the control key and press on the signal name, and we got here the average voltage, which is 2.875. But is that the average voltage for the cycle or for the whole signal here, which is from 0 to 10 milliseconds? I'm telling you, it will show or will calculate the average value for the time shown on this waveform plot. Okay, so if I made a zoom, for example, now we got 2.7 something. Okay, a zoom, for example, for this portion. So now it's 0 value, and it should calculate 0 voltage if it's really taking consideration of what is shown in the plot. So we will now hover over the name and control key and press again. It's 0, yes. So if you want to calculate any value, you have to consider what is shown in the plot. Okay, average value, RMS value, and average power as well. Let's now return the signal, and now I will show one cycle. Okay, if you show one cycle or different cycle, is the same. I will show one cycle and I will consider it as a repeated cycle, and now we'll go to the signal name and get the value, which is 4.9 voltage as average. Okay, we don't care about if it's correct or no, but I'm showing now examples of how the LTSpice consider the calculation of these signals. You have to be careful. If you have non-repetitive signal, so you have to consider what time you will consider for this calculation. So that's very important, because some users misconfuse this point and maybe consider the average value as the average value for the signal, whatever is repetitive or non-repetitive. Okay, now the last point is to do AC signal, and I'm going to now to replace this now resistor, okay, by a coil or inductor. Okay, and that now I will make AC analysis. What we mean by AC analysis, that means we will make the generator or a power supply here an AC signal. Okay, that AC signal sweeps the frequency from initial value to final value, and it draws for us the frequency response, which is something like Bode plot. Okay, so now let's do that. So I have the inductor here. I think this is like a filter. Okay, we will discover now if it's high pass filter or low pass filter. And now I will keep this one, and we'll go to simulate, edit simulate command, and go to AC analysis. It says what type of sweep you want. I will say I want the decade one. Okay, decade one is good for frequency response. And what's the number of points per decade? Keep it as it is. Maybe, for example, 10 points. What is the start frequency? I will say the start frequency is 0. The end frequency, say 1 mega. Okay, and it says the start frequency must be positive. That means it doesn't actually get the 0. So let's see 1. Okay, and here is my command. This one will be cancelled. Okay, and it asks for the value for L1, so we have to make it like 1 millihenry, for example, and run. So now it asked me to set the value, not the name, of the current or voltage source that you want to sweep to AC1. Okay, so let's copy this, and now this voltage, now I have to click on it and set the value to be AC1. So I have to write it like this, AC1, small letter, and now run. Yeah, it runs now, and it seems that there is 0 dB over the range from 0 to 1 hertz, which is wrong. I want this to be 1 mega ohm. So now let's right click on this. Start is 1, and here 1 mega. So I think 1 meg. Okay, and run again. Yeah, see these now things. Okay, 1 mega, we have to write meg. All right, so now this is the result, but the output Vs is our signal here. I don't want Vs, I want V output. So I have to click here, and yeah, it gives me now the body plot or frequency response for this circuit, which looks like high pass filter. So we have here high attenuation for the signal, and then here we have 0 dB, which passes all the signal. So if I just increase this to be 10 meg, okay, and run it again, so it's now high pass filter. It's very obvious. So for the second one, here is the phase angle. Okay, sometimes people not interested in this one now, but at least we have done the AC simulation or AC analysis. Now if I want to show the body plot to see the maybe high pass filter for different values of L, for example, for 3 values, 1 milli and 10 milli and 100 milli. Okay, how I can do that? First, I have to convert the value here. It's not specific value, it's a name. So I will say L inductance. Okay, and I will write it like this. So you have to define it like this. I will tell the LTSpice its parameter, so L inductor. Okay, and I can give it initial value, for example 1 milli. Okay, and now I want to sweep it, so I can write another command which is called step or sweep the L inductance. Okay, for just 3 points. To make specific 3 points, I have to add the word list 1 milli and 10 milli and 100 milli, and that's it. So now what I have done, I defined the value of L to be a variable. I defined that variable by parameter, and I asked this step function to sweep that parameter 1 milli, 10 milli and 100 milli. LTSpice now will run this simulation 3 times for each value of these and give us the value of, or the results in the body plot here. And so now run it. So we have an error, and it's in the step command because we should write the word parameter. Okay, and let's run it again, and yeah, we got it now. So we have 3 high pass filters. Okay, and these 3 related to each one of these. Okay, so but I don't know if the green one is for the 1 milli or for the 100 milli. So to know which for which, I have to go over the waveform and press. Okay, and the first cursor, it comes on the green curve. Okay, and that green curve, now if I press the right button of the mouse, it will tell me that curve is for the L inductance 1 milli. And now if I want to go to the next one, I have to just use the arrows. Okay, the up and down arrow. For the up arrow, it goes to the next one. Press on the right click, it will give me 10 milli. So this is the curve for 10 milli, and another up arrow, and right click on the cursor, it gives me 100 milli. So this one for 100 milli, and then 10 milli, and then 1 milli. This is how we do the sweeping and also the frequency response generation. So what is expected from you is to duplicate what I have done in terms of circuits and commands and also results, just to make yourself familiar more with all the commands and transient and simulations and also the manipulation that we do just to get these results.